Okay, so if you can get started. Thank you, and let's welcome Professor Shang Qian. Professor Shang Qian is professor in CEE department at Carnegie Mellon University, and also has joint appointments in Hans College of Information Systems and Public Policy, as well as Electrical and Computer Engineering Department. He's the director of CMU's Mobility Data Analytics Center, where he leads interdisciplinary research at the intersection of data science, network modeling, and infrastructure systems. He also founded Traffic Core Technologies, which is in CMU spinoff that commercializes AI ML technologies for infrastructure and mobility services. Professor Qian is an expert in many areas of transportation and infrastructure, and he has done fundamental works in many areas, including large-scale dynamic network modeling and data analytics for multimodal transportation systems, and also intelligent transportation systems. His research combines fundamental tools from statistics optimization and machine learning methods to address challenges in sustainable and resilient mobility. And his research projects have been widely supported by many federal agencies and industry partners, and he serves on major editorial boards for several top transportation journals. So let's welcome Professor Qian, and the floor is yours. Thank you.
Thank you, Maxi, for the great introduction. Just making sure everyone can hear me fine, both in person and online, folks. All right, thank you. Yeah, it's such a great pleasure to be here virtually on Zoomly, talking to you about presenting some of my research in the past few years. And believe it or not, this is actually my first invitation to be speaking at Berkeley, even though my connection with the UC systems, dated back into my graduate studies at UC Davis. That was, I graduated in 2011. Again, that's such a great pleasure to be here. So today I wanted to speak to mainly about my research interest. Is really oftentimes I use two keywords to describe my research. One is network, the other keyword is data, and I want to connect these two pieces by looking at how we can realistically replicate the dynamics of very large scale networks, and especially in transportation systems, transportation networks, with the understanding that there are many different pieces of the network that can be observed in terms of having very high granularity, spatial temporal high granularity data. And how can we leverage the emerging multi-source, multi-jurisdictional, multi-scale, large-scale data to understand the high resolution, high granularity dynamics of the network. So this is really my interest. And with that, and I want to present today a very, rather than going to all the technical details of covering a specific area, I think I only have 25 or 30 minutes or so today, but I do want to present, the flow was mainly on that, I want to speak to kind of general framework. A lot of it I want to clarify. I don't really necessarily have a solution, but more of a throughout some idea, some wild idea, maybe. But then I want to give you a very specific way, even though it's a very naive way, but it's a very starting point. Try under that very general framework and some of the ideas I'm thinking about, and with some specific use cases to demonstrate how these things can be implemented, executed in the real world. And this is kind of what I'm framing today's talk. And the motivating slide is really looking at oftentimes I got so many questions from industry partners and from government agencies. Sean, we know everything about the transportation networks, right? Look at the Google Maps, look at the Waze, look at the Uber data. You have so many data and in terms of very high granularity. Look at the Google Maps right now, the typical traffic flow, ongoing 24/7, any 5 minute, any real time, what's going on the road. They also tell you there's a, police trap, there's a work zone. And then this very accurate information in real time. And what is the missing piece? Why are we spending so much time and discussing all these things I just described? And then my take on this is that kind of leads to what what motivates my work is that I think that its key is the ability to predict. And there it really comes, the prediction comes with two different skills. One is real time, in the sense that can we predict the next 30 minutes or so, or 15 minutes, an hour, how things might look like in the future, right? This is not something Google Map will tell you. Especially under these non-recurrent big events. We know what's going on right now, but can we have the ability, people want to have some certainty of be able to predict what might happen in the future. This is the short term. In the long term, oftentimes we're making very big, drastic capital investment decisions, right? How much toll? I mean, let's say Bay Bridge, you want to raise the toll from $6 to $10. In New York City, charging congestion pricings. We might want to, cut down the road to have some kind of road diet project. What are these, the impact of this, any infrastructure decisions, or maybe even any policies, the travel demand management policies? What's the impact of the very large scale networks, right? This is a kind of, again, that's another time scale. We want to have the ability to predict. Ideally, we want to know what might happen precisely. And these are just a lot of potential use cases that cannot be only based on current data, which Google Map tells you. And now this is the kind of wild idea that I have, is that can we somehow magically, right? It's just a very large language model, and with that analogy, think about what if we can get a very gigantic G function, or maybe G model, foundational, whatever you want to call it. Somehow magically we can enter this black box, some sort of demand estimation, or maybe some sort of supply, right? Road infrastructure, transit, these are the lines, subways, these are the supply. And then we also know something about the demand. Somehow this whole magic box will spit out some performance measure. And that way we can always alter the demand, or maybe alter some policy, then we can test it and then give us the accurate performance measure virtually in any granularity and resolution that we like, right? So this is kind of ultimately what we want to do. And believe it or not, we are doing to some degree part of that. And very traditional, I want to use two extremes as two possible examples. One is the conventional dynamic network model is precisely doing it, which is I've been doing this for many years. And the idea is now we want to use the network model to represent a typical weekday, for example, right? This is essentially saying, now I have collected PAMS data for 2 years, and every Wednesday, I take out the Wednesday data. I assume this is the typical Wednesday, and then I take the daily average across all these Wednesdays in the past few years. And that is considered as one single set of data points, even though it's many data values of data coming from different counts and different speed, different segments. But in the network model perspective, this is still considered to be one single set of high dimensional data where the model try to fit. And then oftentimes right now we don't, as far as I know, there's no very good mechanism to fit a high dimensional large scale data in a high dimensional space, essentially. But the problem is that it's only one single data set, and you can possibly have many different models to fit that data, one single data point in a high dimensional space. But even with that, we don't have a very good way to fit that single data point in a high dimensional space. Number two is a very conventional data-driven approach, right? And rather than model travel behavior, model traffic flow models. And then the assumption is simply saying, now I have many years of data accumulated, and I may be able to use the data-driven approach to kind of infer or predict what might happen in the future. This is feasible. And then, for example, you look at the Bay Bridge traffic, and every single 5 minutes, and with the last 5 years, think about this is a simple case. This is a time series model, and you try to predict, hey, next 30 minutes, next 1 hour, next Sunday, what the traffic volume on the Bay Bridge is. And it can actually, with some model tweak, and then you can fit it pretty well. But the challenge of that data-driven approach is that the model has never seen something drastically different in the past, right? What if the Bay Bridge, we want to charge $10 toll? because historically it never happened. It just that simply cannot model these what if scenarios with that only the data-driven approach only. So my question is that can we build some kind of foundational model, rely on the data, but somehow incorporate a lot of the dynamics of the traffic flow and travel behavior model? So somehow it's a mixture, but then that big G function has to really see a whole lot, has to see a big variations in both the supply and demand in order to learn. It's like a high dimensional space. You have to explore many different parts of the high dimensional space in order to learn this function pretty well. And also, just like a computer science area field, how do you build the dimension, design the dimension, and build the embeddings of that demand, supply, and performance to this input space in this input space? That's a very big question. Like I said, I don't really have a solution today, but I want to start by looking into whether we can formulate the entire network flow problem with the data into some sort of general neural network and machine learning kind of classical neural network approach, where it really creates a very generic way of throwing into any general data, multi-modular data, and still be able to calibrate itself in a very general way. It works with any data. It works very large scale network. It works with any sort of general traffic flow. And if that's the case, then we can start to look into ways to build a better input encoding, embedding, and design all the high dimensional spaces. But that's kind of the goal of today's talk. And I know I took so much time just to give you some little bit background. But the idea here is let's revisit very quickly some of the network model, right? Imagine that you have a very gigantic network, everything's connected. And then the performance that we, as a decision maker or private firms, what they really want to learn is about X, which is link flow, path flow, and system states. Remember, these are all in a very high dimensional space. It could be every 5 seconds, every single row segment, every single possible path, every single location community. We want to know the performance, the flow in terms of link and path. So that way we know pretty much anything we want to know about the system, that we can understand the system, right? The G function, which is I am going to take a little bit of time try to describe what I think of the G function is. Like I said, the demand side, naively, we can use a very traditional origin destination demand, time-dependent origin destination demand Q to approximate the demand. Let's assume this is the one of our input. And then the G function really includes a lot of the user behavior model. And I'll discuss what the user behavior is in this case. And imagine that you have a capitalized N, which represents some kind of supply. Like I said, supply means it's a geometry of the network, whether the bus network, anything that's static about providing services, but also some services could be disrupted over time. That's all being part of the supply side. On the demand side, we have the dynamic OD as demand Q with a high dimensional theta, which is a lot of parameters. The parameter could be the characteristics of the demand, travel behavior choices, how people willing to travel, all these things that can be built into this whole gigantic dimension, high dimensional theta, right? Again, like I said, it spits out the performance, which is link flow, path flow, and the system states. The question here is that we have partially observed link flow, path flow, and the system states. And let's assume that for a moment that we have a very big picture of the supply. And can we build some sort of function that estimates the demand and Q and theta, which in this case, think about the machine learning approach. This is about learning all these parameters that can fit the data. And this is what I call calibration in this context. And once we have this G function, if we do, luckily enough, then we can give it different capitalized N, which is supply. We can give it different demand Q. We can give it different parameters of theta, depending on how you design the theta. Then we can give us supposedly very accurate X, F, and C, which is our performances. So believe it or not, this whole thing, the structure has already been heavily invested in the translation literature. And this is what we related to, not entirely, but related to the classical DTA model, dynamic traffic assignment model, plus some calibration process. Usually we call it OD estimation, dynamic OD estimation. There are many different challenges as to why we, in my case, we want to build a want to tweak the model. As you can see, the very generic framework that I'm going to present in a minute. But the idea that some of the challenges we try to address, these are just some of the challenges, but it doesn't mean to be exclusive. So data calibration process is a very big issue. Like I said, as far as I know, there are some papers and but we generally haven't been doing a very good job of fitting every 5 second, every single row segment for a very large scale network, right? And the counts and speed and waypoints, GPS traces, OD demands, and cellular data. So there are multiple data sources. There's not not yet a very good mechanism to say now confidence enough that, hey, my dynamic network model is able to replicate precisely what all the multi-source data, large scale data can tell us. Number two is, like I said, this is typically based on one single data set. It's what we call the average day, but the model does not necessarily have learned, especially system dynamics, hasn't really learned as much about connecting on the average day, and with all the non-recurrent days, right? Maybe there's a price jump on Bay Bridge tolling, or maybe there could be some very big incidents, maybe sports day or marathon. So some of the very non-recurrent days, we also have the data, but how do we connect all the data? And then in a sense that we can build a day-to-day model for this very big G function. And it has to be multi-class, different vehicle classes, different modes of transportation. Another big issue, which is what we try to address partially here, is that a lot of times because we want to model travel behavior, everything has to be agent-based. But we know, and then in the classical machine learning approach, right, you have to calculate all the gradient. Everything has to be continuum flow, and it has to be flow-based. So that naturally is some sort of a conflict if we directly adopted the machine learning approach to calibrate the entire network, which is the focus of today's presentation, is that how can we do that? To be a compromise between agent-based model which allow us to model the individual agent's behavior versus you also can take advantage of the machine learning approach to calculate all the gradients in a very large scale neural network approach where everything can be calibrated in a very precise way, computation efficient way. Individual user behavior oftentimes will only look at the time rather than looking at the multiple factors and time, cost, and safety incidents. There's many effects that we should consider. And then oftentimes, like I said, this is limited to medium-sized or small-sized networks, which is something we want to address. Next few slides, I want to go very quick, and a lot of it is just in the literature, but the idea here I want to present is that tell you how do we build a G function in a very conventional way. This is not the only way, but it's at least something that we have invested very heavily. One thing is that we can map the path flow to link flow and the system performance, system state C. This whole process is typically we call simulation or network loading, whichever way you prefer. But there is some kind of system dynamics, such as CTM or link queue or double queue. There's many different ways to model that. It's simply load all the vehicles along their path, or in a more general sense, this is every agent has already their behavior or their choice has been determined. Try to load it up in the network and to see the flow in a very general. And this is just telling you that we model parking. It gets very complicated, the network, and we model different modes of transportation, parking, vehicle classes, different modes and things like that. And then wrapping up this F function, right? Remember, this F is path flow. It naturally leads to X link flow and the system states. Well, we have the OD. This is the middle layer where we have maps. This is another function that maps the OD demand Q to the path flow. Well, this is naturally some sort of a fixed point problem where F is actually a function of C, but the F also determines C. So that's a fixed point. But what my point that I'm trying to make here is that for every single OD demand, or either it's agent or flow, regardless how you want to model it, there needs to have some sort of behavior model understanding how each infinitesimal flow or the agent is going to make a choices in the very large scale networks. And this really gets you the F. As you can tell, this is something that we have used in our model. Just want to give some idea. Actually, we provide a list of time, cost, inconvenience, crowding, incidents, and many different terms. It's what we call generalized utility distributed function. So the bigger layer, now we talk about the inner layer, middle layer, and the bigger layer is really the calibration process, right? Once we know how we can map the Q into X, F, and C, now the job right now is try to calibrate all the theta in a way, in a computation efficient and accurate way that we can learn about these parameters using the data. And once we had the X link flow, path flow, and system states, then we can naturally come to calculate all the VHT, VMT, and all energy consumption, because that simply naturally is a result of all the flow. So here's a very general framework. I'm going to talk a little bit about this, and then I'll present to you some examples why I consider this to being very general, right? So on the left, and this is a very classical neural network design of. So essentially, we are trying to model all the traffic flow model, behavior model, all the path flow, link flow, all the system performance, all into one single unified framework. From left to right, this is what we call the forward propagation. So you're starting from some sort of demand, and then I'm not sure if you can see my mouth. Let me see. Oh, that's okay. So starting from the most left is OD demand, and then you would want every OD, like I said, it's either agent or flow. You want there's a mode choice, then there's a route choice, right? Once you have the choice, you try to load it up into the network and then get you the link flow. Once you have the link flow and the path flow, you can calculate pretty much any performance measure you like. This is what we call the forward propagation. And throughout this whole entire process, at any layer, you can actually compare the outcome of that layer with the data you have observations. For example, I can compare my OD demand with my historical OD, either the planning agency might have it, and maybe sometimes we just simply collected data from AT&T and telling us a sample of this OD, right? I mean, you have partial observations about the OD. Or we can look at the link flow layer, where we have the PAMPS data give us some every 5-minute time increment traffic counts, where you have to observe the link flow. You can compare these two. And then sometimes we have pro vehicle speed. So what my point is, on this layer, at any point of this layer, you should be able to compare your output with the observation, where you can calculate the discrepancy, where this discrepancy can be flowed back through this backward process to be able to calculate the gradient of that parameter as part of the high dimensional theta, which really help you to enhance the calibration of the whole neural network. And then you can do this forward, backward way, and then that really take advantage of all the machine learning approach. But I try to simplify this for the purpose of conveying this whole idea. But there's so many challenges that in the problem that we haven't really addressed that I want to clarify. The one example is, like I said, this is how do we compromise this whole process of the forward process likely to be the agent-based model, but backward process has to be flow-based, because you want to efficiently calculate all the gradients. Cannot be based on agent. So we do have many different ways to approximate this whole process. One most promising way that we have been recently working on, for example, is called what we call the differentiable agent-based model. But I don't think that I can get into a whole lot of details. But the idea is that we designed the framework. I want to quickly give you one example. This is what we did in Columbus, Ohio, as part of the Smart Columbus project, and this is giving you some idea. 7 hours AM peak, PM peak, and resolution 5 seconds. We have roughly about 138,000 OD pairs, a number of links, a number of nodes. You can tell this is a pretty sizable network. We also have this many bus routes and bus stops, right? So the data that we have, coming back to this is a kind of really just a one single data point perspective. And we do have 15 minutes traffic counts. by two different vehicle classes. As you can tell, all these red dots on the top, but these are locations where we have the counts by two different vehicle classes every 15 minutes on a typical Wednesday. And the bottom is all the bus stops. We know every single bus run, every single bus stop, what's the on and off, and in-vehicle passenger. So we can get the data from passenger, the transit APC AVO data. It's actually pretty ambitious that we wanted to build a simulation or network loading process that can replicate the data in this dimensional, even though it's one single typical day. But it's the process that it's like I said, this is a generic neural network design. And then we're able to get a pretty reasonable results, not perfect, but there's so many things that we can still continue to improve. But just so you know, you see some of the results. I think the calibration, we're pretty happy. So as part of the project, we want, once you calibrate this G function, right? So that one use case in this case is that, hey, if we build some mobility service to fulfill some of the first mile, last mile trips to connect people from certain neighborhoods to take the fixed route transit services, and how this really improve the whole system performance. This is what we call the prediction, right? And the ability to predict under this what if scenarios. And quickly, again, this can spit out a lot of the very interesting results. I'm not going to get to more details. So this is actually a graph that shows more specific details, actually, shows you how things can be done in one single layer of neural network. And this, I'm taking the very simple case where this is a static traffic assignment. Everything we have done, I just show you the examples, everything is for dynamic, but I just using the static case as one example to show how the neural network can be designed. From the very left, it's every single row segment. You have this link flow, right? And then, we in a very naive way, again, we can apply some BPR function, which is parameterized by alpha and beta. Then that's a link performance function. You can use any link performance function, and that gets you the travel time at the link level. With some distributive function, general distributive function, you can put this together in some sort of a path-based, link-based distributivity, and then goes to path-based distributivity, and then use the softmax, you can get you the portion of how people making choices at the path level, and that then goes to the OD. Once you get the OD, you can get the path flow as another direct mapping, and then with the path, it's you can map it directly to link flow. So then this is comes back to its original input, and this is very classical encoder decoder problem in neural network design. And the most important thing you can tell is there are so many layers that we designed and incorporated all the traffic flow model and the behavior model. And any point on this layer, you can always compare, depending on what the data you have, you can compare the data observation versus the calculated the output from the neurons, where you can look at the differences of the work of the loss, right? And then you can flow back to the original parameter just to calculate the gradient and try to keep moving towards the right direction, where it gets you the ideally zero losses for all these data. And then the idea, again, like I said, this is try to minimize not only the data loss, but also at the same time we try to minimize like I said, this is a fixed point problem in a way to model the travel behavior model. So then we also try to enforce some sort of equilibrium. Of course, you can design whichever way you define your behavior model is, but the equilibrium is just one simple example that possibly can be implemented here. And again, this is one example we did in California SR41 network, and this is pretty. All the data is public, and PAM's data and travel speed, which from INRIX. We have some additional information about we suspect that people may want to make choices not only just based on time and cost, but also based on reliability, which is day-to-day variation of the travel time. Maybe crime or incidents, or income, because different people have, with different level of income may have different choice preferences. So we kind of throw in everything here, and then not only we learned about the OD, but we also learned about this distributive function that vary by different origin destination pair. If you look at the very last column right here, you can tell anything that were marked with small letter A means it's a significant, right? Everything that you can see, what we learn about this model on top of learning about the OD, but we also learn about the parameters for the distributive function, where you think that everything kind of makes sense, and people, generally prefer travel if it's a higher average travel time, then less likely to pick that route. But my point is that you can build any general terms you like, and then you just throw it in there, and that neural network general approach can help you calibrate all these parameters in a way to fit the data. But these are two examples. I don't, we certainly did many other cities and regions and very large scale networks. I don't think I have time to go through it. But I do want to stress that the computational graph, kind of the design, as you can tell, that why do we use it? Because many existing technologies in deep learning can be directly applicable here. Whether this is software packages that we can directly use, or parallel computing, or gradient algorithms, and then we can also apply not only just one single data, but also we can throw in 500 days of data, right? And then along with all the supply changes. And this is precisely exactly that we're working on right now. We can throw in the same network, not only everything I presented to you is one single typical day, but we more ambitiously, we want to throw in many days of data, dynamic data, as well as some data measuring the supply side. So we can still fit the one single model that can replicate the day-to-day process. But we can also separate the training and testing. I think this is training testing in the past that was never very rigorous in network models. But we can also make it more rigorous in a way to avoid some overfitting problems as well. Next, a few slides. I don't think I have a whole lot of time. I do want to take a few more minutes at the end to speak to 3 specific examples to further demonstrate that now this whole framework can really work with any data, not just the traffic count and speed and approved vehicles and either the very traditional traffic data, but this is a kind of one set of data that we use. And we figure we had a project working with a company called Automodus. And this is a company that deployed the cameras at the street and telling us the curbside utilization. And we do know at the curbside street segment level, how many vehicles, what different vehicle classes, what they do with the drop off or pickup, right? How many passengers, and we know all these informations, and then we work with this company through a Department of Energy grant, and then that's actually additional data set. It's not traditional, but if that data becomes available, really tells a lot of information about the people's origin information or destination information, right? And then what the different vehicle classes. So it's not something that we typically have, but it's very valuable information that we can really help us to further enhance the model. And again, I'm not going into details, but the same approach is that as you can tell, this is at the very bottom, this observed curve events is the additional loss function we try to build, comparing to the part of the link flow in this link flow layer. And this is simply adding additional loss values to the whole framework, and we just continue to use the same neural network calibration process to learn about the whole parameters. I'm not going to details, but forward and backward, and we calculate all the gradients by ourselves. And we do see that, hey, this has been implemented in the city of Pittsburgh, informing the city about calibrating this G function, right? And also inform the city about, hey, hypothetically, if you build additional pickup drop-off locations, or maybe raise the prices about the pickup drop-offs, just like everyone now paying extra dollars in the airport, and how would this impact the whole system performance? And then you can see the data calibration process is pretty accurate. But there are, I would just say that it's never perfect. There's so many other issues, which I don't think that I have details times to present today. But I think that overall, I think it's pretty reasonable results, and generally replicates with the traffic flow pattern at the curbside as well. So the second example that I want to tell a little bit more is another set of data that we start to use to think about the value of it. It's actually what I call the satellite imagery data. And why this is low cost or ubiquitous? Because satellite image really covers everything. Right now, it's a resolution where we are able to extract a lot of vehicle counts. Well, in this case, this is not the flow. This is actually the density information at every single road street that we can have the satellite can actually see reasonably well. And this is a kind of coverage of the traffic counts and segments with the speed data. You can tell for City of Pittsburgh, it's very scattered. It really has a lot of data, but it does not really cover every single street, right? So if you have this satellite image, right, it really covers everything except for some of the interchanges that, these are the problem that we have issue with. But most of the streets, as long as the satellite can see, that you can extract a lot of information using this vehicle detection, the image processing, that we can extract the vehicle counts actually in a reasonable, accurate way in terms of different vehicle classes. So again, this is something new to the traffic flow model, the traffic network model, because that's the density information, even that's one single time shot. But we know what time that the satellite took that image. So entering that density, one-shot density information into our model, it really also helps to improve the model. We have a couple of papers to demonstrating that. Again, it's just as easy as adding one more piece to the loss function and just working with one of the layers. You're able to actually calibrate. We show that actually calibrates the model way better than where you're holding everything else the same, but you don't have the density information, right? So I'm skipping it. The last slide is that we did actually a multimodal network model in the city Genova in Italy. And that's a project that we work with Hitachi Rail, where they have operates one single metro, and there are 28 bus routes. Two metro routes is actually different directions. That's why we have two. And we do have some data. We synthesized actually some data, but the OD data is coming from Vodafone, which really give us a starting OD information, right? In this case, we're building a multimodal network, multi-class network. It's the car, truck, roadway, bus, metro, all these blue dots are where the stops are. We do have some synthesized counts and speed data, the real data from Vodafone. And we also have the passenger count of every single bus run, every single bus stop. So we have that information. Again, this is a single day, but it's a high dimensional data that we try to calibrate simultaneously. Again, we use the same approach. I'm not getting into details. So again, like my point is that it's not only that we model the OD, we're able to calibrate the OD to replicate all the multi-source data at the same time simultaneously. But also we're able to learn about the parameter for the distributive function. We're assuming people making choices on different modes and different route choices. There are so many factors that people consider, and we can actually infer these parameters. What's even better is that we also build some theories to conduct hypothesis tests, right? And then not only we want to learn about the parameters, but we also want to know, hey, whether this is statistically significant. So in a way to do feature selection and understanding, hey, what are the many factors that people consider most significantly? So I think that's pretty much everything I want to talk about today. I just want to use this example to tell you that I personally really have been a very big fan of embracing very large-scale multi-source, multi-jurisdictional data, some are emerging. And there's a great opportunity right now. We can leverage this to understand the system dynamics very well, but we do need to build some sort of I call it foundation model. It may not be the right word, but the idea is try to, with this generic neural network or computational graph design, that we're able to incorporate a lot of physics model, right? Here being traffic flow, network flow, or behavior model into this whole computational graph design, such that we can leverage data to learn about things that we we will not be able to fit the data, high dimensional data. But then maybe it's possible we're able to do it. So in a way that we can fit as much as we can, then we're better off by making a better prediction. Coming back to my first slide is that we really appreciate the value and the ability to make a forecast and make a prediction in as much accurate as we can. So that completes my talk today. Sorry I was 5 or 10 minutes beyond the time I committed. But I would be happy to take any questions or comments. Thank you. Mercy, you can still hear me, right? Okay. But somehow I cannot hear anything.
Yes, we can hear you.
Oh, okay.
Thank you.
Yeah,
So,
Martha, hey. How are you?
Manshi, can you see us?
Yeah.
We cannot hear you, though.
Can you hear me?
Yeah, I can hear you. Hi,
All
Martha.
right, Sean, thank you so much. That was great and great to see you.
Oh, thank you. I see you everywhere.
So
How are
I
you
just
doing?
have a quick question.
Yeah.
For people who are using like large scale agent-based modeling like MathSim or Polaris or so
Yeah.
on, is there a way to utilize your methods within those frameworks, or do they have to shift to what you are presenting here?
I technically, I think yes, I get this question a lot, but I'm just hesitating. What's the best way to respond? Since there are so many experts, Monty, you've been experts in simulation too. Well, first of all, let me come back to this open source code link that I encourage all of you to check out. And there are so many examples that we posted. Everything is open source. I hope that you all can replicate everything I have presented today. But I think the key here is not about what simulation tool that you want to use. The key here is to design the forward and the backward propagation process through this whole computational graph design. My sense is that if you use MaxSim or some, by the way, our tool is called MacPosts. But if you use MaxSim or some other tools, I think as long as you have a way to kind of separate the whole process of simulation, if you can separate modularize, this is the right word, the modularize the whole process of simulation being part of the forward thinking, forward propagation, and you also have the ability to effectively calculate the gradient. But that really does take a little bit of time for you to think of how to convert that agent-based model in the forward process to a flow-based model when you want to calculate the gradient. I think this is the key, but I know it's very easy to say that. And a bottom line that I'm trying to respond in the easy answer is so far I found very challenging because the mechanism of calculating the gradient based on for any parameter is very challenging unless you can have a way to modularize your simulation process and be able to differentiate the agent in a very effective way, which is essentially the challenge of all the agent-based model where it's just very hard to scale and replicate the data because of the continuum issue. Yeah, but sorry, I don't have a very good solution for that.
This is great. Thank you so much.
Martha?
Yes. Thank you, Sean. Very powerful work. I would like to
Thank
get
you.
your opinion on you told us the calibrated models that would give us the betas and the gamma of the models. Then when we think about physics-based models, so what I would like to get your opinion on is is there a way to use this framework to better evaluate the new type of models? So how would we discover the new macroscopic fundamental diagram? So right now, as I understand, we are using the existing models humans developed, logic model, fundamental diagrams. However, it would be nice if we could open up the family of models and learn from what are the best type of models. Is this something you are working on, or you have some thoughts about it?
Yes. Yes, Martha, I appreciate that question, and that's right to the point. And I really echo that it's very important to have the ability not to be stranded by one single specific type of model. And I want to use this as an example to maybe further elaborate on what I meant by modularization and maybe computational graph. And as I understand that this is a static case, right? But my point is that this whole design of neurons and supposed to be pretty general, but you can replace it with, let's say you're not really interested in a large model, you can replace the softmax with something else, right? If you don't like the way that link pulse function is BPR, you can replace it by something else with different parameters. But I agree with you. So in the dynamic case, I don't have the graph to show the dynamic case, but right now we use the link Q model and the CTM model. And I think that you definitely wanted to have the ability to expand it to different type of fundamental diagram. Well, we actually some of the work in the Google research actually inspired this work is that they actually look into all the speed measurement data at the road segment and across different cities. They try to train what they call the foundational model that inputs the speed and outputs the speed for the next few time increments. Let's assume hypothetically that model can be ready, right? And I think that we can also design in a computational graph way that model, readily available model that can be incorporated, right, embedded right in here. It's just that every time you update your parameters, your backward propagation, when you update the parameter, these parameters won't be updated. I think this is the whole different techniques that in the computer science the community that has been doing this, and you can choose how to regularize it. You can choose what parameter, what gradient to update, what gradient not to upgrade, and which one that you want to do most efficiently to avoid diminishing gradients and a certain type of data. I think this is precisely my point is that if we can build this whole framework, then we can leverage a lot of the tools or methods that has already existed from outside the translation world.
I agree.
Maybe that's something that I'm not saying this is the only way, but I'm just saying this is a possible way that we might be able to extend our ability.
Excellent. Thank you. Thank you so much.
Thank you, Martha.
Thank you, Sean. So I also have a few questions. So one is a follow-up of Martha's question. So in the graph that you designed here, it's still incorporated quite a bit of domain knowledge, right? So one particular thing is this equilibrium concept and the soft enforcement of this fixed point. So I wonder if this is going to be better compared to, for example, I just tried with a multi-layer, multi-head transformer. Just forget about equilibrium or the fixed point part. Do you think because in practice, behavior may or may not be an equilibrium?
Exactly. Yeah.
So also there's this trade-off between given the training and test data, what you see as the accuracy versus if you find a scenario that's extremely different from the training data set, more kind of domain infused graph neural network design versus a completely just black box design, they may perform very differently, right?
Yeah.
So I wonder, what are your thoughts about incorporating the equilibrium layer or not?
So I completely agree, Nancy. So I don't think necessarily that equilibrium is the way to go. I personally do not think and people to generally has the tendency to do it in a very selfish way, but not necessarily it's not necessarily true in general case, right? Especially under these, and the one example that we're working, some of the work we're working on right now is to understand the non-recurrent pattern, right? Certainly there's not equilibrium because there's nothing to equilibrium on. So I think the whole point of this, and that's why I want to show this is the approach that we do not have to. That's just the other equilibrium, softly enforcing equilibrium is just one example. If you think that equilibrium is the way to go, but if you don't think this is the way to go, like maybe you are trying to build everything based on non-recurrent data, there's no equilibrium, then you can still design. Well, this graph might not be necessarily what I'm referring to, but you can. My point is that you can still design a computational graph approach to fit your need, but generally following the same, forward backward kind of pattern, and then just that you have to design it in a way that the forward backward can update your gradient of the parameter. I think this is feasible. Actually, we're doing this right now. Only looking at a few days, actually 100-something days after a very catastrophic road bridge closure, and we try to model that non-recurrent day-to-day process. I think this. My bottom line is it's possible without considering any equilibrium constraint.
Yeah, thank you. That's very helpful. Yeah. Any other questions?
Did you want to ask a question?
Yeah, I had a question. I put it into the chat. If you could go back to slide 6, on the surface, the formulation looked like a static assignment, and so I was wondering how time gets incorporated into this.
So I think you said that sorry, I didn't get. You said it looks like a static, right? Your question is how the dynamics of it is being incorporated. Is that correct? Yeah. So yeah, I think it's not the static. I don't meant to present this. I meant to present this in a very general way. So the idea here is that the link flow, path flow, state C, and then Q demand, theta, everything is a high dimensional space. It can be static, it can be dynamic. Actually, we adopted this approach that for all the example, you accept the SR41 network later on the example you see. Everything else is actually a dynamic case with a 5-second resolution. So this is just a vectorized way to present a very general approach, but yes, it can be both dynamic and static.
Okay. Yeah. Okay. Thank you very much. Thank you, Professor Chen. Thanks for the great and inspiring talk.
Thank you. Appreciate it.
Yeah, for the audience, if you have more questions, feel free to maybe reach out. And we're going to conclude today's session. Thanks so much.
Bye.
Thank you.
Thank you.
Bye-bye.